Okay, so this time we're going to go a little bit more advanced. It's probably where, yeah. It's definitely more advanced than what I've been doing recently anyway. And it's a great book. Look at this. We could decide. I've also got like the the hardcover. There it is. Look at that. Except it's backwards. Oh well, never mind. Yeah, and I spoke to Sandy and he said it's cool to use it on a stream, so even better. But if you do want to purchase it, I'm going to put it in all the comments. I recommend you do because it's really cool. I'll pop it here. So you can follow along, but I will have it on here, and then ideally even just follow along as well. It might be a good idea, but as you can see, it's type level programming. Yeah, it sounds a bit more daunting than it is, to be honest. It's actually quite nice. It's not as I have experienced in a lot of. Oh, let me move this a little bit closer. Come closer to me. I'm going to turn my mic up. It's kind of hard to tell. Yeah, these audio levels on this program I've got are rubbish. Don't tell you anything. Anyway, let's... what was I going to do? Yes, so this book, boom. It's not like as intimidating as you might think. Yeah, I found it like good. I mean, I've got stuck on. I think I was going through it again, and I kind of got stuck on. Well, not stuck. I managed to do it, but I wanted to have a deeper understanding of what was going on in certain chapters. I think around chapter 5, I got a little bit confused. But fear not. Boop, 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 boop. Oh look, it's got so yeah, boop, 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 boop. Acknowledgement. Sorry, introduction. Boop, boop. What are we going here? So this is just sort of showing how things happen. Fundamentals. Okay. So what's the first bit? Is that readable? I think it's kind of readable, isn't it? Well, let me just switch over to here, so then that just sort of doesn't bother me. I'm just looking. Well, let me know. I think it's within reason, isn't it? If I flip this over as well, so if I get my Emacs going, I think we're on a good stead there, aren't we? I think we're winning, really. Okay, so the way I'm going to go through this is the way I pretty much read it. So I'll get confused with the big words, and I'll try and convert them into how I think about them, which is probably not going to be very terse, and Haskell's going to be annoyed by me, but never mind. What can you do? Yeah, and then just work through the exercises. It's kind of the key. I think if I demonstrate how I reach certain, again, we're going to very much my favourite type holes, Mr. Mrs. type hole. Use that as often as possible to help me with my life in general, I think. So let's do it. We'll start here. So the algebra behind types, isomorphism and cardinalities, which is cool. This one's good. So killer feature and pattern matching, and made possible by algebraic data types. So when we say an algebraic data types, it's literally one of those, or one of those, whatever. Being comfortable understanding and manipulating this algebra is mighty superpower. It allows us to analyze types, find more convenient forms for them, and determine which operation, example type classes, are possible to implement. So to start, we associate each finite type with its cardinality. So this is what this chapter is about, cardinality. The number of inhabitants it has, ignoring bottoms. Well, we can always ignore the bottoms. So consider the following simple type definitions. So we have data void. Okay, should we start typing these out? Why not? Except it's probably going to complain at me. No, it won't. Okay. I can't remember if I've bought in. I think we should be fairly reasonable. illegible. Look at that. Yeah, definitely don't do that one. There. Illegal. Oh, okay. So I don't know why that's an illegal one. I don't recall. So you can't bind unit to unit. Okay. Well, we'll ignore it. And then, oh yeah, like so we can do. I see. I'll set that up because I don't think. Oh, okay. So it's been happy with that. Yeah, I don't know. Don't know what happened there. Oh, hey, thanks for the follow, Blimecoat. Blimecoat. Hey, Vlad, how's it going? Yeah, I'm going through the Thinking with Types. What a cool book. So, yeah, I've basically been playing with it. Got to, I actually, ages ago, got to chapter 9. And then I recently went over it again. And I got to sort of chapter 5. And then got a bit lost with, what did I get lost with? I think we were doing something maps. I forgot. Something. Yeah, got stuck. Oh, did you die as well? Cool. Well, the hope is that 2 brains are greater than 1. So maybe we'll work it out together. It's hard because the thing is that some people have finished it. And there is the option to sort of cheat and look. But I just found that I was doing that. And that kind of sucks, you know. It's like, was I really getting the full understanding? Probably not. I was cheating. And I kind of like knew the answer, but I didn't know why it was the answer. So then that's just memorizing, isn't it? It's not really learning. So let's go on to cardinality. So void has the 0 inhabitants. So this one. Okay. So it has the... I'm going to turn this music down. It feels loud. Oh, getting heavy with the in-depth pianos though. Chill out. Come on. I'm trying to learn here. Right, here we go. Yeah. Is that... Actually, let me know if that's big enough. I think that's big enough. Seems big enough to me. But I've not got a screen that you might have, so... So void has a 0 inhabitants. So it is assigned to cardinality 0. Which makes sense. Well, it doesn't, but... Yeah. So that means 0. There's literally nothing to it. So that's cool. And then thus the unit type has 1 inhabitant. Okay, so that makes a little bit more sense. So its cardinality is 1. Cool. But bool has a cardinality of 2, and corresponding to its constructors, true and false. So if we look at this, cardinality 1, cardinality 2. Okay, all nice and nice for now. So we can write these statements about cardinality more formally. Yeah, so we can literally do it like that. Yeah. Any 2 finite types. So, yeah, I guess finite is like that are not infinite types that have the same cardinality will always be isomorphic. So 2 finite types that have the same cardinality. Okay, so if they've got the same, so say like bool has 2. And something else has 2, they should be isomorphic to one another. So that's interesting to think about, isn't it? An isomorphism between types S and T is defined as a pair of functions to and from. Cool. I mean, this is literally going to do nothing, but we'll do it anyway. I don't think I'm meant to type this stuff out, but I'm going to do it anyway. So S to T and from is going to be the other way, isn't it? T to S. Cool. I'll go like that. We'll comment it out by pressing the wrong key. There we go. Because obviously I'm just declaring types, which is no good. Such that composing either after the other gets you back to where you started, which makes sense. So, you know, if you're going to go from S to T, then you could go back from T to S. So if we look, to from is the same as ID, and from to is the same as ID. And then if we look at, let's do a bit of this. Is it like that? Yeah, it is, except it's opened it there, but never mind. Here we go. So if we quickly look at the type of ID. Cool, so we just see it's A to A, so you know, so if you use ID, there we go, it just returns us 3. So doing a to and from, because it's taken it from S to T and then back from T to S, Well, clearly that's going to be the same as doing an ID. You know, they're almost, yeah, cancel each other out. So we sometimes write an isomorphism between types S and T as this little symbol, which is kind of like an equal, isn't it? There it is. Oh, almost. That's cool. Didn't know it'd even work. So where am I going to go? Go back here. Cool. So if two types have the same cardinality, any one-to-one mapping between their elements is exactly these to and from functions. But where does such a mapping come from? Anywhere. It doesn't really matter. So just pick an arbitrary ordering on each type. Okay. So not necessarily correspond. Okay, so ordering doesn't necessarily respond to the odd instance. And then map the first element under one ordering to the first element under the other. Rinse and repeat. Okay, let's see how this works then. So I guess that's the explanation. And now the bit that we like is the code. So we've got a data of spin in my case, and that's either going to go up or eep or down. Okay, that makes sense, doesn't it? So by the arguments above, we should expect spin to be isomorphic to bool. Yeah, because if we look, that's got exactly the same cardinality, didn't it? So if you look at bool, look, 1, 2, and it's exactly the same, isn't it? So spin is just, it's got two constructors, up and down. Okay, so actually, should we put like a little I've got to spell it properly as well. Cardinality. Cardinality, yes, of 2. What I'm going to do is call it Cardi. Like Cardi B, the rapper. There we go. Cardi 2. Then I don't have to spell it out and get stuck on it every time I have to spell it. There's always ways around things. So bool to spin. Cool. So so now we're like what we were talking about before is any two with the same cardinality can interact with each other, can't they? So I think this is a demonstration of that. So to spin 1, and that's a bool. What am I going? Bool to spin. Okay. And then pick it up for me. Thank you. Oh, bless the Haskell language server for saving my life. It's probably a bit extreme, but yeah, it's gotten so much better. Sorry, just having a bit of a sip of water. Yep, definitely. I mean, it's so, even with things like later, I guess we'll start doing imports, and you can do imports and type holes. Oh my goodness, the advice it actually gives you is improved like there's no tomorrow. I think in another stream someone actually showed me like a crazy, I think, yeah, we just created a data type and then created a function with its data types in action. It just filled in the whole function. I was just like, what is going on? It just looked like amazing magic, black magic. So if we do false, that's going to equals up. I guess we could do the other way really, but it doesn't matter. And then if we do spool and we true, and that would equal down. Okay, so that makes sense, doesn't it? That's that way. And then we can go the other way, which is spin to bool. Cool. I mean, I'll copy that because, you know, especially when it's like that. There we go. Spin to up equals to false. Oh, what's it go? Ooh, I've definitely not copied this right. Look at that. Cool, that's fine. Yeah, and that's going the other way, isn't it? If we look at it, so we've gone from bool to spin, and now we're going from spin to bool. And clearly, they can quite happily relate to each other because they're both of a cardinality of 2. Okay, that makes sense. So, however, note that there is another isomorphism between spin and bool. I feel like I know Sandy said it was like cool to use it, but I feel like I should have like a link to it. Maybe like every 5 minutes I can just hey Gil Christian, how's it going? Maybe I can just do this every 5 minutes. You know, like you get adverts in America every 5 minutes. I can just do that. And then, hey, bye. Anyway, probably a bad idea. Ah, cool. We're just we're just going through the book by Sandy McBride, Thinking with Types. Well, I'm kind of glad. No, let's not mention anything to do with America right now. It's a bad time. It's a bad time to be mentioning America. So I've been told. Yeah, so we're going through this book. I've gone through a little bit already, but we're just going to go through it again and then see how much I well, I like that. That's a good little emoji, that one. I need to zoom in to get some better. There we go. Let's have a little look. Yeah, that is rad. Emote. Oh, a comrade. Oh, you're a... Oh, that's following Dos. Oh, yeah, he's another streamer, isn't he? He's really good. I'm not up in the world of... Right, okay. Stop doing it, Vince. Get back to action. Mr. Sidetrack. That's what I should have called myself. So, however, note that there is another isomorphism between spin and ball. Yeah, which is what I was saying. We can literally go the other way, can't we? So in this case we went false up, but we could have gone true up and false down. Yeah, so that makes sense, doesn't it? So for that reason, we're going to copy it and just do that. So what should we turn out? That'd be true, that'd be false, and that'd be down, and this would be up, and then everything would be all over the shop. Yeah, something like that. Yeah, it's meant to be lockdown in the UK, right? So, you know, which means Mr. Sidetrack, I'll steal that name from you. Yeah, literally take it. That's all I do. I type for about 10 seconds, talk for about 4 minutes. What can you do? That's just how it is. Yeah, anyway, I was going on about the lockdown in the UK. So today's the lockdown. You'll be hearing in the background lots of fireworks going off, right? Yeah, so clearly what people do in lockdown, you know, just set off a load of fireworks. We went to get some medicine for my wife. Just went up sort of the top of a hill where there's some shops. Absolutely rammed, like just wandering around, loads of cars parked everywhere, just, you know, like nothing has happened. Great lockdown. I think people have just clearly given up, haven't they? They should have just made the initial lockdown worse. You know, it's like Haskell, isn't it? It seems like you're doing a lot more work at first, but it pays off in the long run. Wow, should have done that with lockdown, shouldn't we? Anyway, enough of politics, and we're here to get away from that. So, which of the two isomorphisms should we prefer? Oh yeah, so which? Well, I'd guess any. Does it? Does it matter? In general, for any two types of cardinality of n, there are n unique isomorphisms between them, which makes sense. So it's to the power. To the power. As far as the maths goes, any of these is just as good as any other. That's the kind of maths I like. Any of these are as good as any other. So, and for most purposes, knowing that the isomorphism exists is enough. Right, well, it's the end of this then, isn't it? As long as we know they exist, we're winning. An isomorphism between type S and T is a proof that, for all intent and purposes, S and T are the same thing. Okay, so let's have a look. So I had it up here, didn't I? So we're saying that the types between S and T and S. So S and T is a proof that, for all intent and purposes, S and T are the same thing. Okay. So they're gonna, in terms of cardinality, I assume they might have different instances available. But this is more a statement about Haskell's type class machinery. Yes, okay, so it is from that level. It's not the fact that, you know, up is exactly the same as false. It's just saying that their representation in terms of cardinality, I guess. Yep, this is about the equivalent of S and T. Isomorphisms are a particularly powerful concept in the algebra of types. Cool. So throughout this book, we shall reason via isomorphisms. Or isomorphism. No zzz at the end, just isomorphism. So it's best to get comfortable with the idea now. Yeah. If you've got any questions, ask. I'll probably be asking lots of questions myself, to be honest. I hope you can answer. Because, yeah. in case I'd assume everyone that's watching this has a good idea of isomorphism. If not, I can sort of explain it. I mean, yeah, when I think of isomorphism, it's basically a value that's not set or concrete. So it can be any value until set. It's kind of the way I think about it, I think, which is potentially not good without showing. Should I show? An example could be, yeah. So we'd have, let's use x instead of a, because that could probably, yeah. So that's an isomorphic function, but isomorphism, that's a different thing, isn't it? I'm probably getting things confused. But yeah, so a to a, that's isomorphic, but isomorphism is something different. Hold on, knowing that isomorphism exists. So the isomorphism, actually it's going from one function to the other is the isomorphism, isn't it? Yeah, okay, so I got it wrong way around. Why have they got the same name? Oh no, isomorphic, isomorphism. Oh, it's the S and the M that caught me out, isn't it? Anyway, yeah, this is the thing that gets me, I think, all the time. It's so much to remember, isn't there? 4 years in, still. Come on, get in there. God damn you. In the language of cardinalities, some types correspond to addition. This bit. Oh, I remember this bit, and I read this and I was like, what the hell? This is so cool. Okay, so some types correspond to addition. So this is a sum type. Okay. The canonical example of these is either AB, which is either an A or a B. Okay, so either A, B. As a result, the cardinality, remember, the number of inhabitants is either A, B is the cardinality of A plus the cardinality of B. Oh, this is where yeah, things get, okay, it might not make sense straight away, but it will. It's okay, so if we think of either, let's put this down, because this is cool. So if we think of it like that, so either A is just like A plus B, okay? So as you might expect, this is why such things are called sum types. That's where things come from, sum types. Literally, when I read that, I was like, oh, wow. It's so simple, yet so good. The intuition behind adding generalizes, to any data type with multiple constructors. The cardinality of a type is always the sum of the cardinalities of the constructors, of its constructors. Okay, so let's have a look. So here we've got another data type. I mean, we can see there's an explanation for that. So where are we going to go? So let's go like that, this A, and we're going to go that B, and the other bool. Is that what we're doing? The other bool, yeah, so that's cool. That's happy with that. Yeah, so obviously they're going to have like a different cardinalities there, but let's do it. So we can analyze deal's cardinality. Okay, so deal AB. I don't know how this is. Actually, I'm going to do it in two parts in hope that things, yeah, that's working out better. Especially when you're on the wrong line. Let's go to the beginning. There we go. So that's like that. And then the second bit here. And we'll pop that. Evening, Gaffer. How's it going? Yeah, we're going through. I should explain. Oh, it's time for an advert. We're going through Thinking with Types by Sandy Maguire. I don't know why I was going to say Maguire, like the Irish Mac or Scottish Maguire. And it's basically type level programming. Sounds intimidating, but I don't think it is. I've done a few chapters already, and it's quite fun. And we've literally just started, and we're looking at cardinality of types. And you kind of come in at the right times. I think right now we're just explaining that these have an isomorph. If something has the same cardinality, so if you look at spin and bool, this has a cardinality of 2, so 1, 2, 1, 2. Okay, and any functions, or sorry, data types that have the same cardinality are like have an isomorphism between them. So if you bool to spin. So bool to spin, that goes from false to up, true to down. And then spin to bool is like the other way around. And then you can have the other options where you do true, you know, so if we started, look, we did false up, but you can have true up, false down, down false. So like the opposite way round type of jobby. And now, so then we get to see, we're looking at either, and if, because they're actually, when you, where was it? Here we go. So either AB is like, is a cardinality of plus the cardinality of A plus the cardinality of B. And then it's also why they're called sum types, because it's A plus B, which is, you know, if I had like a brain, it's like, whoa, okay, that makes sense. And we're literally just got onto this bit, and we're looking at deal, and then we're analysing its cardinality to work out what is what. And here is it's kind of like breaking it down a little bit. So deal, deal lab, deal AB, yeah, and we'll move that a little bit forward. There we go. So it's A plus B plus bool, and then we know that bool is a cardinality of 2, so it's A plus B plus 2. I'll put a little space there. Actually, I'll like align it underneath. Okay, so that kind of makes sense so far. It all, what is it? This seems a bit more advanced than what I'm used to, or at least more theory. I don't know. No, I don't think so. I'll be honest. I think you might, like, if you like hold on a bit, because I think this stuff feels maybe a bit of theory, but there's some good examples of it in use, and then it'll make sense. This bit is basically trying to work out, there's a thing called cardinality amongst types, and we know that some types, like either, ends up being, the reason it's a sum type because you add that plus that cardinality. So we're only really just looking at a concept of cardinality. There's no like real use to it or anything as yet. It's literally we're just looking, and then these funny looking things is literally we're just like looking at that and just going, okay, there's an A and a B, so we do A plus B, and then we've got a bool here, so plus bool. So whatever A is plus whatever B is plus a bool. That's literally all. So, you know, I think, hold on, see, but I mean, I can understand if it gets a bit too much. Yeah. Sorry. Well, no, actually, if it gets too hard, ask. That'd be cool. Don't worry about it, because I'm, you know, I do find this thing daunting as well. So don't worry about it. Ask, you know, any silly questions, and then we'll try and work through it. So we can also look at cardinality of maybe A, because nullery date constructors are uninteresting to construct. Okay, so like nothing, that's a nullery, is it? There is only one nothing. That's true, there's only one nothing. The cardinality of maybe A can be expressed as follow. Okay, so if you look at maybe A, yeah, so nothing, okay, so nothing, much like when we did bool and true and false. True can only be true and false can only be false. So maybe is nothings is going to be 1, and then it's A is going to be whatever it is. Okay, so that makes sense. So dual to sum types are the so-called product types. Now we're stepping it up. Well, we're not really stepping it up, but we're discovering another side of it. Okay, so again, we will look at the canonical example first, the pair type. Yeah, so like a tuple. So A, comma B. Okay. Analogously. What does that mean? Compared in certain respects, typical in a way which makes clear the nature of things compared. Okay. So comparing the cardinality of a product type is the product of their cardinality. Okay. So AB, when it's a comma, it's like A times. To give an illustration, consider mixing fractions of the form 5.5. We can represent in Haskell via product types. Okay, let's try and do this then. follow along. So, to be honest, it's probably quicker to not copy it. Yeah, because it copies it a bit weird. But it's cool. We'll get it going. There, 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 and then I'm missing a value, which is cool. Definitely not a question mark. Oh, I love my... Look at that. So you do that, delete one, it gets rid of them both. I'll beat you, don't you worry. Cool. Okay, so we looked at mixed fraction A, so we've got a data type called mixed fractions. It has an A, and then it returns a fraction, and its constructors are mixed bit. Oh, excuse me, which is the word A. Numerator, which is an A, and then denominator, which is also an A. And oh, here we go. Now we're going to see some Haskell language server. Let's have a look. What should we do? We'll bring it in from data.word. I think we're going to do it. And it's not going to be happy because all my false and trues. Yeah, hold on. Why did I do save? It's because I've got my own up here. It's gonna be funky. So what I'll do for now. Okay, it's gonna be happy now. Yeah, it's already imported. So if I tried creating my own on top of the existing one, but look at that. Just imported it for us. What we created the import, except I've still got errors. Duplicate. Oh, okay. Yes, of course I've got duplicates. If you're gonna sort of copy things. Oh, you can also... Hi, Blind Coat. Did I say already? Oh, I've already said hello. Sorry. Oh, my goodness. I think you can also turn on the no implicit prelude extension. Oh, ooh. Oh, what, as a flag? So, within here. Yes. Oh, of course. I think that's what you mean, isn't it? So, like a flag. No implicit prelude. Well, let me know. Oh, we've got this sort of 10-second delay where I'll just hang out and wait for a potential response. Yep, then it'll be like pure script. Also, then it just, yeah, so it just says prelude doesn't exist. Wow. So is it literally as you spell it? I assume. Yeah, like that. Should we try it? Well, we're going to now because I've done it. Let's go there. Let's go. You know, I can get rid of this, can't I? Well, I still get the error. That doesn't matter. What am I doing? Don't press those. Press these ones. These are the buttons you want. And then it's going to load. It's loading. See? Action. Action happening. We'll shut this. Okay. We're unhappy about something, which is somewhere else. Okay. Oh, it's not a module's... Oh. Wow. What did we do wrong? I had faith in you, Blind Coat. I had, you know... See how I put myself on the line there. Look what happens. Is it lowercase n? So I guess... You know what we can do? We can find out. Oh, so it can only be a language pragma. Because the other way you can do is like this. I spotted. What does it give you options? Set. Is it normally like W? No. Is it W? Yes. Is it in there? No. No implicit. No. No im. Maybe. Oh, here we go. I think it's here. Maybe it's with spaces. Implicit prelude. Yeah. Oh, I've just... No, I haven't said it yet. So... oh, hello. So if we go like here... We'll go back to the cabal. Cabal. Oh, the magic W. Yeah, I think it'll be alright. I'm going to try this. Oh, if the... Yeah, okay. Let's just try it like that. Let's give that a go. Let's do it. Let's reload. Let's see. No, it doesn't like it. Oh no, it does like it. Ignore the arrow down the bottom. It's doing something. No. It's worth it. We gave it a go. I'll have to look it up. Let's go here. Oh, V. Right. Where are you going back? Come on in. B. E. B. B. E. E. B. X. Save. Okay. We'll reload it. Yeah. I'm sure it would have worked. No. I think we're definitely on the right line, but I just don't want to spend like ages trying to work it out. Well, I mean, it clearly exists because when I look, you see down the bottom here, it found it. So I guess we can end of buffer. Just enter. There we go. So we've set it in here. So I guess look, we can set it in here. Bool. Yeah, and it'll be happy. Would be especially, yeah. There we go. So it's happy there, you see. Yeah, so I think it works. It's got to be bought in from Cabal. So Cabal. I don't know how you say it. It's got to be bought in a slightly different, I guess. But that's for another one. Doesn't really matter. What we'll do is just this. I'll work around it. And then the other way I'll work around it is I just put ticks everywhere. So I give it well, if I can find a tick. What has happened to my hands? There we go. I just added a tick, and that sort of gets away with it. Where were we? So there's some errors which aren't showing, but it'll be these. Let's use this infamous tick. I could use a multi-cursor, but I didn't. There we go. So we're happy. We've got a green tick. Yay! Okay, so where were we? We're looking at this, which is here. So let's have a look. So we worked out that this is a product type. These are a product type, which was... Actually, I'll copy that in before we get to deal. There. And then beginning. There we go. So yeah, so A to B is like A... Sorry, A comma B is like A times B. Okay, I'll leave a little gap because we've looked at that. Let's go down a little bit. Sweet. And now we're going to look at a cardinality of something like this. And this is what's behind it. Oh, I bet one of the questions is, what is a cardinality of word 8? I think that's probably one of them from memory. Mixed fraction A is like word 8, obviously, times A times A. Oh, there we go. Look, the answer's right there. Let's put it underneath. Oh. I thought it was one of the questions, but no. That was just wishful thinking. Let's do it like this. Yeah, that lines up. That's nice. So word 8 is obviously 256. Okay, that's the cardinality. Because if we go into word 8, there's 256 values, I guess. And, yep. And then times whatever A is, and times another A. Okay, so let's work that out. I think we'll get some in the task. It'll kind of like give us things to try and work out, and then we actually create values to these types. Okay, so proved. Okay, hold on. We were reading. So an interesting consequence of all of this cardinality stuff is that we find ourselves able to express mathematical truths in terms of types. Or just you wait. We need that mind-blown thing coming up in a minute, because this gets really interesting. So, for example, we can prove that A times 1, okay, is equal to A by showing that I'm isomorphism between A and unit and A. Check this out. Okay, so prod unit 2. Is that what we're calling it? Yeah. And that's going to be a weird type definition. A, 2, and it's return a tuple of A and unit. Okay. Let's find it for me. So close. I thought it was going to type it out for me. No. Sometimes it works, sometimes it doesn't. A, and that's going to equal, much like the type, like that, isn't it? Think about it. Let's go. Actually, let's just, sometimes I need to bring this down. It's good to have it in view, but it's also good not to. And the next one is going to be, what's the next one? Prod unit from. Okay, sorry, of course, it's the other way, isn't it? So, prod unit 2, which is now from, and that'll be the other way around. So we'll have a tuple of A, comma, unit, and that'll be an A. Yeah? So let's do it again. Prod unit from, and that will equal, oh, I didn't, I should have done this first, shouldn't I? Yes. Whoa, hello. Whoa, look at that. Didn't want it like that. There we go. And that just equals A. Okay, that makes sense, doesn't it? Looking at oh, excuse me. Looking at the types, it's pretty self-explanatory. But here we go. Here we can think of the unit type as being a monodial. I'm doing it again. Modial. Right, ignore that word. For some reason, I can't say it. So, it's like just put these words just for me, so I can't say them. Identity for product types. Look, I've just totally ignored it, so I don't have to say it. In the sense that sticking it in doesn't change anything, because A times 1 is equal to A. Yeah, so okay, we can pair with as many unit types as we want. Likewise, okay. Likewise, void acts as a module, okay, I'm going to get, bear with me 1 minute, bear with me. Google has this feature that can help me, hasn't it? Except I have to go onto Google. Yeah, oh damn it. I don't think DuckDuckGo pronounce it for me. No, what do you mean? I was hoping to have like a little I'm going to say it for you. I don't know why I'm finding it so hard. Monodial. Let's skip that. Oh, I'm sure this word's going to come up loads as well. I can read it. Maybe I've got dyslexia. Maybe that's what it is. Maybe I'm dyslexic. That's why I've been struggling all this time. I've just never realised. So I clearly can see it, but I can't read it. Anyway, to convince ourselves this is a trivial statement of A. I'll translate. Do you reckon translate? Let's do it. Except I don't think you'll be able to hear it, but I will. And I'll repeat it in the exact same voice. There we go. Google Translate. It's definitely not French. It's English. Oh, it doesn't matter. It'll just say it, won't it? Okay, hold on. Speak it. Monoido. Okay, I'll do it again. That's not helped me one bit. Monoido. What the? What? Google. Monoido. Monoildo. How do you say it in Spanish? Monoidal. I prefer that. I'm going to say it in Spanish from now on. Monoidal. Or in English. Oh, in French it's monoidal. Honestly, go on Google Translate and knock yourself out. It's actually quite amusing. Monoidal. Monoidal. Yeah, monoidal. Okay. Sorry. We went off on one again. So the trivial statement A plus 0 is equal to A can be witnessed as an isomorphism between either A, void, and A. Okay, so let's have a look at that. Monoidal. God, what have I done? I should have used Google Translate to teach me how to say that word. I was going to end up saying it. So, what have you been doing? Monoidal. Cool, thanks. That's really helped me. What am I doing? To A. Okay, I'm just copying what's on the right, sum to unit. We're going to go left of A. Yeah, that makes sense. So obviously left is going to be first. And that's just A. Okay. And then we'll do the same again. We'll do that again. And this time we're going to go right V. Aha! This was cool. Also, is it going to find it? I can't remember where it comes. Oh, it's fine. Oh yeah, it'll be happy with that. Cool. I like this one. Absurd. Absurd's really good. Well, yeah, it's absurd obviously, but there's an explanation in a minute. Well, it should be from. Yeah, and this one's a little bit easier. A to either A and void. Well, it can only return one thing. And that can only, literally, can only return left if we look at it. Monoidal. Yeah, okay. I figured this wouldn't be happy. And what is it doing? No, we'll import it from void. Cool. And then it'll complain. Couldn't match expected type. Okay, but I think it explains us why something. Yeah, I think. Oh, hold on. I think I'm potentially. No. Okay. I think it explains. The function absurd here, which is what we're looking at, has a type void to A. It's a sort of bluff saying, if you give me a void, I can give you anything you want. So it's just saying that V isn't. But obviously V. What is V? V is void. Right there. So what's wrong with you? What do you mean you couldn't match void? So look, it wants a void. And if we look in here, well, V's a void. Okay, well, watch absurd. I'm going to give you a V. Oh, is it a different void we're dealing with here? Is it the wrong absurd? I assume that's probably the issue. Where did we bring it from? Data.void. Is it using the wrong void then? Maybe we should bring in void from here also. Because I'd... void? Void? Yeah, there we go, it's happy now. Yeah, it was using the wrong void. That's fine. Did I define my own void? By accident? Where did I do that? Oh, of course, right there. This is why streaming's good. I still want to do streaming as like... yeah, it's not going to work, but if it could be my job, and then I'd have sort of 8 or 9 people watching, and then when I make mistakes, often, then people are going to go, you've actually declared it yourself, Wally. And I'd be like, oh yeah, of course, there it is. And it'd help me. Only one catch is I'd probably be the only one getting paid, so I don't think that'd go down too well, would it? Okay, back to subject. Monoidal. It's a sort of bluff saying, if you give me a void, I can give you anything you want. Yep. This is a promise that can never be fulfilled. But because there is no voids to be had in the first place, we can't disprove such a claim. So let's have a little look as to why. Well, so either A, void, yep, would return A. Okay, so if it's left of A, there, that return A. If it's right, which is a void, which it's not going to happen, then it's going to return this absurd of a void. So that's why it's like, it's not going to happen. Function types also have an encoding as statements about cardinality they respond to. Let's have a look. Okay, yeah, this good. This bit's good. Exponentialization. See, I can say that word, but not monoidal. To give an example, there are exactly 4 2 squared inhabitants of the type bull to bull. So does that make sense? Why bull to bull might have 4? Well, I'll demonstrate. Where's my bull? There's my bull. So from bull, you're basically saying bull has 2. We know that it has 2. So if we're going from bull to another bull, then the isomorphism to get from one to the other is going to be obviously 2 to the power of 2, which is here. Look. So that's our 2 to the power. That's all like the different examples that you can do of a bull. Oh, sorry, would that be a bull to bull? Yeah, I'm doing there from ball to spin. But ball to spin would do exactly the same thing. That has the ball to spin would have a cardinality of 4 also. Okay. Am I right? 2 to the power of 2. Yeah. So 2 times 2. So of the type ball to ball, these functions are id, not, const, true. Oh, const true, const false. Oh, okay. Let's have a look then. We can't really. No. I don't know what I'm just saying. Let's have a look. Try as hard as you can, but you won't find any other pure functions between balls. Oh, okay. Yeah, I get you. So there's no other function that. Oh, yeah, as a single function. Yeah, so id, that makes sense, because whatever you give it, it gives you back the same thing. Not, that makes sense, because it just returns you the opposite. Const true, yeah. Let's have a look, actually. Let's have a look at this. There we go. So if we look at const, it takes 2 values, and it returns you the first one. So if you do the type of B to ball, which is yeah. So if we then go false. Hold on. Oh, if I don't, const, which is okay. Poop equals const true. Okay. That just returns. Why is it doing that? Oh, there's a firework. Try as hard you can, but you won't find any other pure functions between balls. So why? Let's have a look. Okay. I understand idea. I understand not. I understand, but const true. Because if we look, okay, let's have a look at the type of. Well, okay, we know not. Prelude ball to prelude ball. Okay, that's fine. But then const true is beta ball. But if you pass it, so const, you pass it. A, B, and A. So if you pass it 2 values, it just returns you the first one. So how come? Is it because I haven't got a show? Let's do true and that. So const true is of the type. Oh, of course, yeah. Yes. Oh, but so it just returns a ball. So, but when b equals ball, then the function is ball to ball. Yeah. Yeah, I think that's the idea. Yeah, because if we looked at the type when we did just const true, that was b to ball, which, but id or not does ball to ball. But then I don't understand the. Yeah, I'm a bit confused with that one. I don't know why it's confused me. So I guess when we called it, I thought here it just returned us like unit, but it's of the type ball at that point. A, B, A. Ooh, other way around. I thought it'd return us true. I guess it just doesn't show it. That's probably the idea. Let's try it on something else. Yeah. Okay. Yeah. That's the reason. Okay. So it does make sense. You see, look, it does return like the number. So in this case, it would just return, but it's not printing it out, which makes sense. Okay. Confusion averted. Try as hard as you can, but you won't find any other pure functions between balls. Okay. More generally, the type A to B has cardinality of B summed with A. Okay. Oh, sorry, powered. So B to the power of A. Which just might be surprising at first. Oh no, but it does make sense. Because when we were looking at ball to ball, yeah, it's like bool to bool is 2 to 2. So that'd be our bool, which is a 2, cardinality of 2, and then our A is another bool, and it's to the power of 2. So yeah, it does make sense. It always, okay, so whilst this might be surprising at first, it always seems backwards to me. The argument is straightforward. For every value in an A, yeah, because I guess it feels like the A should potentially go first to the power of B, but it's actually the other way around. So for every value of A in a domain, we need to give back a B. So for every value of A, we need, so yeah, so if there's like 2 of these, so true, false, we need to give back a B. Okay, but we can choose any value of B for every value of A, resulting in the following equality, which is, oh, what is it? Okay, hold on, let's have a look. So for A to B, well, it's going to be B times X, which is B to the power of A. So however many times, A is the number of times this is going to happen. And then, yeah, so I think that makes sense. Oh, it will, but you can, oh sorry, but you can't print it because someone said you should turn off the prelude. Is that, oh, is that because I've turned off? Oh, okay, what have you done? Should print. We've turned, okay, hold on. Let's get rid of the whole session. I like it. That was good. Is it going to load? Yes. Actually, we don't need to load that file. We can just do. Yeah, that's it. So I was going around in corners going, what the hell? Why is this not working? Right, okay. Well, I thought you were meant to be here to, like, you know, can work it out together where we got stuck. You're just confusing me. Oh, are you kidding? It happens. It's cool. We worked it out in the end anyway. I say we. It was just me sat here. Yeah. Okay. That's all right. You can keep going. Try and sabotage. I mean, I'm confused as it is, so it's only going to... well, actually, it's probably clearing things up. You know, so it's like double negatives. That's what's essentially happening. So we've got an exercise. We've got an exercise. Here we go. So we'll do... what is it? Exercise. What are we on? 1.2. If I put a 1.2 I. Yeah? That makes sense. Cool. Determine the cardinality of either bool, maybe bool to bool. Whoa, this is going to be fun, isn't it? Okay, let's grab it. I reckon we've got this. I reckon we've got this. So, we're going to have to like split things up, aren't we? So we know that if we look at either was like a product, wasn't it? Okay, so we've got, we know that bool's 2. And we're going to times by this stuff. Okay. And then I think that's right. Oh, and then we got to do it to the, which way around is it? It's to the power of whatever that is. And bool's 2, so which way around is it? It was B to the power of A, so it's going to be 2 to the power of whatever the result of these is going to be. Hold on, was either was times, wasn't it? And so look, yeah, so yes, it's a product, and this is also a product. Okay, so I think we're doing good. And then it's going to be 2 times. And we're going to have another, maybe I should put, actually I'll do, this could be our times, because this X is not helping anyone. Oh, ignore the comma. And then maybe bool. So that's going to be, maybe was a plus, wasn't it? Because it's a sum type. So, I'm going back up here. Where does it give it to us? Yeah, so that's sum, which is Maybe bool is 2. Is it 2 plus 2? Maybe bool. Was there? There's a hint up here as to what maybe something was. Maybe, here we go. Maybe A. So maybe 2 is... I think that's right. Maybe bool 1 plus 2. Yeah, so 1... Oh, because of nothing. That was it, wasn't it? So nothing's 1. And then the bool's 2. That makes sense, doesn't it? So we've got here... So we've got all this. Here we go. We can add them all up. Next line. So we can work out... We can go 2 times. Yeah. And then we're going to go... so 2 times 3 is 5. What might... How can I like undo that comment? I can't. It's live and it's done. So 2 times 3 is 5. I was honestly thinking of the something else, of the Radiohead song, isn't it? 3 plus 2 is 5. No, 2 plus 1 is 5. Something like that. Okay, and then we can work out this one, which was the A. There, yeah. So then we're doing the B. So that'd be 2 to the power of 12. Yeah. So that's our cardinality, which is... I forgot how... was it some type? I thought either... Oh, we're Tic-Tac-Toe. I thought either... I did work these out before. So if I ever fail, where's either? Maybe. Some. So yeah, so we've got either... Oh, it is a... Ah, so okay, so we're getting even worse now. So this isn't times at all. This is plus. Okay, alright, well... At least it's a little bit lower, isn't it? 8. Okay. 2 to the what is it? That isn't it? 256. 256 is our answer. Actually, I should just hold on. Have I done it the right way around? I'm having like a little sort of like, huh? Where did it explain it? Where is it? Where are you? I had like a nice little explanation before. Oh, I've totally lost it. Tic-Tac-Toe. Right there. No, it's B. So B to A. So we're going totally the opposite way. Yes. Have I got it right? Hold on. Oh my goodness. Okay, A to B. There's our A. A is 8 to B. And then we're going to do B to A. So I did have it the right way around. So it is 256. Oh my goodness. You know when you just doubt yourself? I think that's my whole experience. To 8. So it is 256. Go back. There we go. 2, 5, 6. That's the cardinality of that type. I mean, yeah, if I'm wrong, let me know. But I'm pretty sure that's right. Apart from the fact that I was doing... I think it feels a bit... It feels like this should go around here somewhere. That feels a little bit better. Yeah, I think we can just have our answer be here. Don't know why I just aligned that. Cool. So we did that. So the inquisitive reader might wonder whether subtraction, division, and other mathematical operations have meaning when applied to types. Indeed they do. Oh my goodness. But such things are hard. Ah, good, because this wasn't hard enough at all. So if not impossible to express in Haskell. Oh, hard or if not impossible. Okay, subtraction corresponds to types with particular values removed, whilst division of a type makes some of its values equal, in the sense of being defined equally rather than having an EQ instance which equates them. I mean, that in itself, yeah, I feel like I need to read it again. Subtraction corresponds to types with particular values removed. Ooh, okay, whilst division of the types makes some of its values equal, in the sense of being defined equally rather than having... Yeah, let's not do it. Basically, that's what it means. It can be done, but it's hard. So we'll just stick with with plus and with sum and products. In fact, even a notion of differentiation in calculus has meaning in a domain of types, though we will not discuss it further. Thank goodness. The interested reader is encouraged to refer to Conor McBride's paper, The Derivative of a Regular Type in its Types of One Whole Context. Here we go. You know, like truth or dare. Well, my truth is I can't read papers. I don't know why. I just, yeah, they're too intimidating to me. Every time I see a paper, I'm just like, whoa, there's just so many crazy words in there. Yeah, and you've clearly seen my ability to pronounce simple words. Not very good. What are we? Here we go. So, example, tic-tac-toe. Cool. I said earlier that being able to manipulate the algebra behind types is a mighty superpower. Let's prove it. Imagine we wanted to write a game tic-tac-toe. The standard tic-tac... Now, I remember this part. It starts off going, and then it goes, whoa. Okay, so imagine we want to write a game of tic-tac-toe. The standard tic-tac-toe board has 9 spaces, which could be naively implemented like this. Okay, so we can literally just represent a board of tic-tac-toe. Oh, I mean, I probably don't need to copy it because you don't use it. But let's do it anyway. Come on. Be enthusiastic. Yeah, and then it gets easier. Boop. Let's do some of this. I think it's just K, isn't it? No, it's not. What was it? Was I R? No, it wasn't. I forgot. I forgot what it was. Okay. Box center. Bottom right. Cool. So, not this scenario again. There we go. We fix that scenario. Yeah, so we can see. So you think tic-tac-toe? There's going to be 9. So you got top left. Actually, let's just do this quickly. Tic-tac-toe, 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 tic-tac-toe. So we get images. There we go. So it's 9 squares, isn't it? I'll zoom in. So we're dealing with 9 squares. Hence, top left, center, top right, mid, bottom. Okay, so that makes sense. So we've represented our tic-tac-toe as a type, and this is how we're doing it. While such things work, it's rather unwieldy to program against. If you wanted to construct an empty board, for example, there's quite a lot to fill in. Yeah. Oh, do we want to fill it in? Let's do it. That'll do. Happy with that. Oh, what's wrong? Oh no, of course I'm not happy with that. Now I'm happy with it. That makes sense. Okay. So to create an empty board, you obviously tic-tac-toe has 9 constructors, so you have to pass 9 along. And yeah, it can be an A. Okay, that makes sense. Yeah, so we're saying tic-tac-toe is the A is maybe bool. Whoops, if we do that. So we're saying that that's maybe bool. So here it's maybe bool. So we're filling them all up with nothings. Which, yeah, it works, but it is a bit, yeah, doesn't look good. So writing a function like check winner turns out to be even more involved. Well, yeah, if we want to check winner, we're going to have to like, oh my goodness, we're going to have, oh yeah, I wouldn't even like to think about it if it's like this. So rather than going through all this trouble, we can use our knowledge of, get ready, we can use our knowledge of algebra of types to help. The first step is to perform a cardinality analysis on tic-tac-toe. Okay, so tic-tac-toe is tic-tac-toe of A is A 9 times. So A to the power of 9, okay, or A 3 times 3. Why has it gone from? Oh, yes, because it's like there's 3 and there's 3 times it happens, so that's 9. Okay, so and whatever A is, and then for our instance, A would be 1 plus 2 again, so it's 3. So it's 3 to the power of 9. We're getting good at this, eh? So when written like this, we see that tic-tac-toe is an isomorphic to a function 3 to A. Oh, okay. Here we go. That makes sense, doesn't it? Because that's literally the same, isn't it? Yeah, because when we looked at it, it's B to the power of A. So that's like our B, and that's our power of A. Or in this instance, it's A to the power of whatever this is. So we can represent that by the tuple of 3 and 3, which is 3 times 3, because tuples are products, to A. Or in its curried form, because if we look at it when it's curried, because this is this, basically it's this. Yeah, that one's interesting, isn't it? So you can go from here. Okay, check this out. So if we go like this, we'll pretend that that's a function. Okay, so that's that, and then it's and its curried version is 3 to 3 to A. I guess it'd be not bool, especially not S. Okay. Of course, 3 is any type with 3 inhabitants. Perhaps it looks like this. Oh, okay. Oh, okay. So we're now sort of stepping away from this. We're trying to say that 3 is a different data type. Okay. And then we're going to derive all of its their constructors. We'll go like this, and we'll do deriving like this. Okay, that's fine. Okay, so we can see we've got the same. We're getting the same cardinality here, aren't we? So we're doing 3, 1, 2, 3. Okay, so that's well, essentially here it's representing what our 3 is. And we know that it's 3 times 3 makes our 9, because there's, 1, 2, 3. Because these are cardinality ones, because there can't be anything else, much like nothing. There's only one representation of 1, it's 1. And 1 of 2 is 2, and 3 is 3. I don't know why I went through them all. Just in case you didn't get the first one, I went through all 3. So, yeah, you gotta punch it home. Due to this isomorphism, we can instead represent tic-tac-toe in this form. Get ready. Get bloody ready. This is when minds are about to be blown. So we've got a data tic-tac-toe, and we're going to call it 2A. Okay, so it's the same like the first one, and that will be a tic-tac-toe 2 again. And this time, instead of having all the instead of having like the 9, do you remember, like this? I had all those, but instead of having that, we can simply represent it by a single type, which is of especially if you can't spell it, 3 to 3 to A. I could probably just have all that on one line. There we go. So, does that make sense? So we're creating, because we did that tic-tac-toe before, and we knew that there was 9, it was 9 times, well, 9, because there's 3 of each row, okay? And then we split that up, instead of having 9, well, it's basically 3 times 3. And then we know this has a cardinality of 3, so then we can do from the isomorphism of 3 to 3, that's doing 3 times 3 there, and then to our A. So we're literally doing A to the power of 9, which matches this cardinality of what we had originally. So this has the same cardinality as this, okay? Which, on the face of it, you think, what the hell are you on about? But when you kind of like break it down and go through it, then magic starts to happen. And thus simplifying our, and thus simplifying our implementation of empty board. Oh, this is like clever. So we know now we can do empty board 2, and that has a tic-tac-toe 2, and we're going to give it again. We'll do the maybe ball, not a book, a ball, and we'll do empty board 2. Yeah, so that equals where are we? Tic-tac-toe 2, and this time, so we know from memory const was ABA, the type, wasn't it? There, another ABA, there, and a nothing. That's going to be happy. Actually, let's, how can we break it down? We can do this. Whoops. Let's have a look what the type of this is. Will it give it to us? Oh, at least like give us something. Come on. Normally it should sort of say this hasn't got a type signature. It should be. Actually, I could have just hovered it there, couldn't I? Yeah. Okay. Here we go. Our type level was there. So poop, which is const, is a B1A, B2A. Okay, so it expects 3 values and it'll return us an A. Which if we look at, okay, let's break this down. So we look at here, we expect a value 1, 2, A, but there's 3. 1, 2, 3, 1, 2, it has to go, hold on then, let's try this. Whoops. Whoops. Yeah, so this basically would return us nothing, and then that would be const nothing as well. Here we go, we got better now. There we go, now we're matching, aren't we? Look. So we have B1, B2, maybe A. Yeah, that makes sense. B1, B2, maybe A. Okay, so that makes sense. Sometimes, this is where like, before, without the Haskell language server, trying to find all this stuff out just wasn't so readily available. Yeah, you can't just, you'd have to go into the repo and bring it in, try and work it out. But here, look, just a little hover, or even like just the warning, it's telling us what it is, and then how come it's that, and then how it matches this function. So actually, when we can use our thing here, and we can load what is it, chapter 1 I think I call it, chapter 1. There we go. And what do we call it? We called it empty board. I've created a show instance, haven't I? Yeah. Oh, or is there? There isn't. I could do that. Let's do it. Where's our tic-tac-toe 2? We'll derive show here. Whatever's happened there. And then where's our other tic-tac-toe here? And then here we'll do like that. No, it won't be happy. Oh, ooh, hold on. Why not? Why aren't you happy? No instances of show for. Oh, okay, yeah, because it's okay. This might not work then. It should work because I've got the show on 1, 2, 3. So okay, let's find out. Let's do that. Oh, I forgot the name of the function. It's empty board 2. Okay. Empty board 2. Okay, it's just wishful thinking. But it's giving us a board of maybe ball. Okay. But the board will actually be just a tic-tac-toe full of nothings. Anyway. Oh, I don't know where I've gone there. Let's go back. Let's go back. Keep it going. Keep it going. Such a transformation doesn't let us do anything we couldn't have done otherwise, but it does drastically improve the ergonomics. Yeah, so if we compare that with this, I mean, clearly know which one we'd rather use. Yeah, it's exactly the same functionality, but instead of passing each individual value, we're passing these two threes, these functions, into an A. Okay. By making this change, we are rewarded with the entire toolbox of combinators for working with functions. We gain better compositionality and have to pay less of a cognitive burden. Let us not forget that programming is primarily a human endeavour, and ergonomics are indeed a worthwhile pursuit. Your colleagues and collaborators will thank you later. So when this all makes sense, you can thank me. Okay, I'm ready. CMDV on Twitter, shout out. Actually, you should thank Sandy Maguire because he's the one that's done this. I'm merely the messenger. I'm definitely not the creator. Okay, so Curry-Howard isomorphism. Good old Curry. Our previous discussion of algebraic. Should we do a bit of that? I haven't been doing any of this, but I'll tell you what, my non-streaming version of these files are a lot neater. Our previous discussion of algebraic relationships between types and their cardinalities can be summarized in the following table. Yeah. Oh, I kept going up and down, didn't I, to try and work out what was what. But we knew that. Okay, so I end up ignoring the middle one. I just looked at the algebra and the type in the end, because that's a bit I understood. The logic obviously is like a mathematical thing. I just went, yeah, like that. But an algebra of A plus B is like the type either AB, and that's because it's a sum type. This is a sum type. That's a product type. Sorry. A like a tuple, comma B. So that's A times B. And I guess if it would be A, comma B, comma C, it'd be A times B times C. This, so an isomorphism from A to B is the same as B to the power of A. And we've proved that when we did this magic. When we were able to reproduce that in this format. Okay. And then A is equal to B, so an isomorphism is the same as A is equal to B. A void is like bottom and 0, and unit is like 1. So when we did nothing, that's like 1. Cool. So this table itself forms a more general isomorphism between mathematics and types. Yeah. It's known as the Curry-Howard isomorphism, loosely stating that every statement in logic is equivalent to some computer program and vice versa. Oh, okay, so this is like making a connection between maths and computers, I guess. So it's saying that, whatever you do in here, well, in fact, it has an underlying logic and an algebra to it. Yeah, something like that. I'm glad I'm reading it out, because if I have to explain this from scratch, there'd be trouble, wouldn't there? So the Curry-Howard isomorphism is a profound insight about our universe, the whole universe. I like that statement. Yes. So Haskell is the entry to the universe, hence my background up there. See, that's the universe. That was my idea. I didn't get that from this book, but I'm going to say great minds think alike. Yeah, I definitely can't take this. Yeah, I can try. It allows us to. Oh, I think that was part of the deal. I can't of this book. You can't basically resell it or make it out as you did it. And I said honestly, if you watch me read it, it'll be very apparent to the viewers that I definitely did not write this book. Which I think I've probably proved now. There's some more stuff here. Ooh, I don't know if I'm going to be able to do this. What time is it? Okay, we're going to keep going. This table itself forms a more general isomorphism. Yep. And, oh, where was the universe comment? There we go. Insight about our universe. It allows us to analyze mathematical theorem through the lens of functional programming. Which is like, this is the bit that's like cool. Because I guess in reality, this is like fun to learn. Yeah. A bit later, you see some more stuff that would be more useful in production, for sure. But I think it the idea behind it is it teaches you how you can represent things differently. I don't think you're going to necessarily think, oh, this is cardinality. Or maybe you're meant to think about that. But I think once it goes into gadgets and things like that, then you start seeing like production worthiness of these types of things. And like I said, I'm definitely not, and it's cool that you're learning sort of mathematical theorem, I guess, but I don't see it like that personally, because I'm allergic to two things: mailing lists and maths. So I've joined the wrong programming language, because it seems that mailing lists is like the go-to way things being communicated, and maths. So yeah, but it's cool that the fact that that you could do this stuff in, I guess. No, you can't. There's no type system. I was about to say you could do it in JavaScript, but you bloody can't. Yeah, so it's cool. What's better is that often even boring mathematical theorems are interesting. Yeah, when expressing types. Yeah, that is a bit. This to me is more interesting than that. Like, for sure. I think of all the little things I can do with this, and that I just go, oh, that's an A, and like a V and a B, whatever that means. So, to illustrate, consider the theorem a to the power of 1 equals to a. Okay, well that makes sense. We know if a times 1 is going to be a. When viewed through Curry-Howard, it describes an isomorphism between unit and a. Yeah, I was going to say that's literally unit or ID. Yeah. Said another way, this theorem shows that there is no essential distinction between having a value and having a pure program that computes that value. This insight is a core principle behind why writing Haskell is such a joy compared with other programming languages. Yeah, I think that it is a joy once you start digging deeper. If you can I've happily written Haskell for a while without really getting too in depth on this side of things. But that's the thing that's always really attracted me to Haskell, the fact that I'm not necessarily very good at this side of things. So whilst I'm doing Haskell, I'm also learning this stuff on the side, which is like, I don't know, there's not many other languages that are going to allow that, is there? If you think like big production languages, potentially, I can't remember if I was having a discussion with someone else, but it's potentially also a bit of its fallback, isn't it? The fact that you get all this expressiveness, and it can sort of make engineers like look for almost like chasing a mathematical theorem, or you start looking for the beauty within the code almost, and you abstract things away so much that in the end you just create this thing that's like wonderfully great, but in production you're probably one of 3 people in the world that will understand it, which is then of no use, but it's bloody beautiful. So yeah, that's the thing that's so enticing with Haskell. It's so easy to potentially chase rabbit holes, isn't it, and keep going. But I think maybe, and that's probably what the whole argument between, the whole way to write Haskell, if it should be simple or not, and all that bollocks. For me, it's like any other language. Just, I don't know. It depends on your team and how do you plan on moving forward. A lot of things that happens is any language. It's not just Haskell. People come and they're like really advanced, and they write stuff really quickly, and it's really complex, and then for some reason or another they sod off, and then the company's left with this code base that no one can really work on, and then they end up having to rebuild it or whatever, or something. They write something, an abstraction that seems sensible but is really complex, and then further down the line it's like, oh, we should have just done it simply and expanded from it. So you get those sides of having your 10 times developers or going, I shouldn't class a 10 times developer in the same bracket as someone that's advanced at Haskell, but it's remembering that it's too. I find that Haskell can be quite easy to do that. Because it is mathematically based. It's kind of like, it's almost like, oh yeah, check this fucking crazy thing I can do. Check that out. It's like, wow, that is crazy. Like this. It's okay. This is we're not like pushing a boat out here, are we? We're just kind of ability to write this in a nicer way by making it a function. That's interesting. That's like useful, isn't it? You can think of uses for that, but I guess it's when you start really pushing the boat and going much, much, much further down the rabbit hole, there has to be some sort of level to to not. And that's probably why it's harder for people to get into Haskell, because I think this stuff is more, I'm like 4 years in and starting to do this, so it's kind of the stuff that you want to know later. And I think if it was in a code base, I'd be able to explain it better than if I had to sort of do it like this. I think maybe, I don't know, it's hard. It's like an attractive thing and a distraction as well, which I don't know, which is now we're coming to a distraction. Here we go. This looks like it has lots of things. Oh, I've got to give a proof. Oh no, I don't want to do any of these exercises. It says proof. That's something to do with maths, isn't it? Said another way, the theorem shows that there is no essential distinction between having a value and having pure program that computes that value. This insight is a core principle behind why writing Haskell is such a joy compared with other... Oh, I already read that. Sorry. Here we go. Using Curry-Howard to prove a to the power of b to the power of c equals a, that is provided function of type bca to bc to a, and one of make sure to satisfy equality to and from IDs from and to ID. Do these functions remind you of anything? Let me look. With a tuple there, do they remind me of anything? I don't know. I don't think they do. You know what we can do though? Maybe Hugel. Oh no, it'll remind Hugel of something. Come on, Hugel. What is it? Uncurry! Oh my god! It should remind you of something, shouldn't it? Oh, that's clever. So B, C to A is, so you give it a tuple of B and C, and then you go B, C, A, and then you return it at A. So that's its value, second value. So it's a function of B, C to A. So yes, the function expects a B and a C, which you're going to give it via a tuple, and it's going to return an A. I'm going to see if there's something there. Ah, there is some examples. This, why, yeah. The whole of base should have examples. Every single function, I think. Sorry, what a request. They should, I'm telling you. Uncurry plus 1 and 2 is 3. So let's have a look at the type. Yeah, so that makes sense. We're doing a function which takes 2 values and returns. So that's exactly what C is. It's a function, C. That's what add is. It expects 2 values and it returns us a third. So there's our first value, there's our second value, and that would return us 3. Okay, so that's uncurrying. And then you get another one. So you uncurry with I don't know what that's called, but it's $, which is like a bracket. So show and 1. So it's literally going to do show on this side and then 1 on that side, which is going to convert the 1 into a string. Okay, that makes sense. And map. So we're going to map uncurry and max. Oh, okay, so we're going to do it on every single, and then a max expects 2 values and it returns us the maximum of this. So if we look at that, it's literally going to convert this tuple into a single value. So the max of 2 and 1 is 2, and the max of 3 and 4 is 4, blah blah blah. Okay, so we get that. So we get uncurry. So if we look at the types, uncurry, and then uncurry, and I guess this would be currying because that's going the other way, isn't it? If we look, yeah, So I guess that was uncurry. And then if we go to another, yes, and that's curry. That's essentially what it's doing. We're this exercise, okay, I'm going to cheat so bad, is we're basically doing it by doing this. I think that's what it's saying to me. Lying so bad. It's probably because I don't. Yeah, so curry converts an uncurried function to a curried function. So it's going the other way around. Yep. Which makes sense. So yeah, it takes a tuple and returns a C, and then there's two values. So when we look at it, first expects a tuple, and it returns it into a C. Oh, I guess it's hard to give it more examples, isn't it? But yeah, and then so that becomes our A here. This becomes our B, and then we grab the first, which is A, and then that returns us the C, which is why we get 1. Okay, so make sure to satisfy the equality to and from is equal to ID, and from and to is equal to ID to each function. Remind you of anything from prelude. Yeah, well, it's like uncurrying. That's what we're doing. And the cardinalities are going to be those. And yeah, is there? I can't remember. Hold on. I don't think I ended up doing these exercises. Give proof of the exponent law that a to the power of b times a to the power of c equals a. Oh, okay. So that's kind of that's just doing what do you call it? I forgot the name for it. The same laws as you get when you with monads and things like that. Oh my god, I have forgotten the name. Anyway, and prove that this is equal to that. Yeah. I'm so cheating. Sorry. But if you know, if you'd like to prove that to yourselves, I just believe it. I'm like a blind mathematician. I'll blindly believe that. I mean, that looks good to me. And I forgot the word for it. Hold on. We even did it in the last. I'm gonna have to do it. Oh, I can't spell. Where's my? Oh no. There we go. Monad laws. There's some monad laws. Not identity. Maybe it's some functor laws. Associativity. Yeah, so it kind of looks like associativity, doesn't it? Oh, I was thinking of composition, I think. Let's have a look at functor. Yeah. Oh, isn't that what we just looked at then? I think we were looking at associativity, Oh, okay. Let's have a look. I think you might be right. Haskell distributivity. Yeah, there. Oh no. Okay. Law. Maybe. I don't know. I was that or the. So I don't think it's quite. Oh mate, where can't you just show me the laws? Where are they? No. Yeah, things like compose and the other ones. Yeah, this is the bit that I've always it's always gotten me. I don't know. I guess maybe it's my lack of academia or any mathematical background. But I understand all this stuff in use. Oh, here we go. We were looking at them there. There they are. These are literally the laws, and we were only looking at this last week. So we've got the identity law, composition law. So which kind of like, if we look at that, that's a law of composition, isn't it? If we look at it. So FG and F map G to F, which is pretty much looks like this, doesn't it? From what I can see, yes. And then potentially that's also similar. Yeah, looks like it. Okay, I'm going to skip those because that was enough. Oh, there's more maths. Whew, okay. Well, I'm not trying to dodge a bullet, aren't I? Who am I kidding? But to be honest, this is like the most hard theory side of things. After this chapter, you get a lot more code from memory. This is like the first bit. I guess it's like learning. You know, when you sort of look at the Haskell book when you first begin, it does bring in a lot of sort of I guess algebra, linear algebra. God, yeah, it brings in like a lot of concepts that might be a little bit confusing. I don't know. Yeah, that's usually how things start out. But this is a lot nicer. I mean, we've not got totally lost. I think this is the only exercises that proving things to myself. I think here's in the name, isn't it? Curry Howard. It's currying and uncurrying. Anyway, a direct corollary that any... Let's have a look what that means. I have to do this a lot. This is why I don't read Haskell papers too. Yeah. A proposition that follows from and is often appended to one already proved. Okay, so it's a plural. A proposition that follows from and is often appended to one already proved. A direct natural consequence or a result. Okay. Oh yeah, so the result that any two types with the same cardinality are isomorphic is that there are multiple ways to represent any given type. Okay, that makes sense now. Although, you'll see I use a dictionary a lot. Although you shouldn't necessarily let it change the way you model types, it's good to keep in mind that you have a choice. Yeah, so again, let's go back to the code. You know, it doesn't mean let's go through your code base and change bloody everything. But it does mean that, you know, you do have the power to do cool things like this, where instead of having that, you know, you can minimize it to a board, which is a function of 3 to 3 to a, which is going to represent, because we know that each 3 can represent, the type 3 can represent 3 values. So the cardinality of those is 3. And then because you're doing it from 3 to 3, which is the cardinality of 3, an isomorphism of 3 times 3, which is 9. And then you know that there's 9 values in your board. And then the A is going to be whatever you pass it along. So you've created 9 squares of the board by a function. That's pretty damn interesting, isn't it? I guess you wouldn't see it like that, but they both function exactly the same, but they just set up differently, which is cool. So yeah, so it has its uses for sure, and I guess if then you see it, it makes a little bit more sense. Where was I? So yeah, so you shouldn't necessarily let it change the way you model types. It's good to keep in mind that you have the choice. Yeah. Due to the isomorphism, all the representations of the type are just as good as any other. However, as we'll see in page 170, I'm not going to click it, it's often useful to use conventional form when working with types generically. Okay, this canonical representation is known as the sum of products and refers to any type of the form there. This one. I've seen this before. You get there's a similar one actually in linear algebra to work out the. I ended up learning some linear algebra just because I on my journey to doing functional programming, I did some machine learning, and then you have you end up doing a bit of this. And I think there's a guy called I think it's called Andrew Ling that does is like really popular in the Python. I guess he mostly does it in Python, but yeah, he teaches logical regression, which again sounds really big, but you just remember it and then you spit it out every couple of years, and then makes you sound intelligent. But logical regression is just when you see the way you imagine logical regression is, you know, when you want to work out the optimum value is basically like a funnel, and it's just going boop, 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 boop. It bounces side to side until it gets to the optimal. It never actually reaches 0, which is the optimum, but it works out. So that's how essentially a lot of machine learning is. It's just, you can imagine like a 3D funnel, and all this is your data, and you're just trying to go down to it until something is equal to the same. And that's logical regression in a nutshell. Which actually, when you think on the top of it, it's quite hard, isn't it? But when you use it, that's it. The theory and the use of it, totally different things. You could just use it, logical, because you end up doing logical regression. A simple form of that is when you have a plot chart of say ages to people's illnesses, for example, and you can say that, or when they're more likely to die, and then you have this plot chart of, so generally it kind of like will go up, so you're more likely to die the older you get. So you have your plot chart, and then logical regression is basically grabbing all those values and drawing a straight line between them, and then you find your mean, as in like what's more likely. Maybe I should do one of these as well, because there is oh sorry, I've totally gone on a rant, but I've not had full time to play with it. What's it called? Torch? Yes, here we go. There is a Haskell. It's really cool. There's basically what's it called? PyTorch, I think it's called in the Python world. And there is PyTorch, and there's literally a Haskell version of it. And the guys, I'm on their Slack channel. So nice, honestly. I wish I've spent more time doing a bit more, but I'm gonna probably spend some time on this. Because that'd be really interesting. My idea of what I wanted to do, which I didn't get time, is I wanted to do some image recognition using something called YOLO, and I think someone had something close to it. But yeah, so I was basically going to try and use YOLO to do image, and YOLO does not just image recognition, but it'll do video recognition. So it can best predict what items things are. So yeah, I thought, wow, that'd be really good. But the problem is, I wouldn't really want to demo it till first I understood this library, and then secondly I got some sort of an example so I could show. So yeah, might be a few years yet. Anyway, back to maths. That was another segue. It's like the shut up, Vince, get on with it. So we also make this stipulation that all additions must be represented via either. No. So the big E, don't skip again, means addition. So this symbol is addition, okay? And the II means multiplication, not like II, captain, is not a sailor. So we can read this as addition on the outside and multiplication on the inside. Okay. We also make this stipulation that all additions must be represented via either. All addition, okay, because we know either's a sum type, okay, and the multiplication via that, yeah, and that's a product type. Don't worry, writing out the rules like this makes it seem much more complicated than it really is. Whew, you don't say. All of this is to say that each of the following types, what's going on? Got to run. Yeah, cool. Thanks for coming in though. I'm probably gonna end it soon anyway. So yeah, well, if you want to come along next time, I don't know when I'm going to do it. So I guess if you follow, you'll get an email now. That's the only thing I can do. But thanks for coming. See you later. I don't know what I'm looking at. Oh, I'm looking that way because that's where the chat is. I should have gone. Thanks for coming. See you later. I just imagine. Oh, I think it just sends you a little bit loopy doing these streams, talking to yourself. I'm like, oh yeah, shut up. Keep going. Don't make it worse. So unit, either AB, either tuple of A to B, tuple C to D, or not 2C, A and B, C and D, either A, We make an exception to the rule for numeric types, as it would be too much work to express them as sum. Well, yeah, because you got to get all values. It's the same when we did, was it char? It's like 256. So if we're going to go numerics, it's going to be loads. But neither of the following types are in their canonical representation. Okay. Oh, they're not in their canonical. So hold on, their canonical, let's have a look. So, why is that not a canonical? Oh, and that isn't either. Is like canonical, does that mean like it's, oh. It's not a sacred book. It's not the church. According to our ordered by canon law. You're not helping me. That's not help me. Canonical. Canonical. I kind of almost canonical feels like it's when everything's like done, but I mean, I could be totally wrong, couldn't I? Canonical. Text JSON canonical, no. Generic programming, okay. Definition I should have wrote. Canonical definition. Whoa. Is it related to? Of, related to, or forming a canon. It's not that one, is it? Canonical. Okay. Conforming to the rules or acceptable procedure. Okay, that sounds more like it, doesn't it? Conforming to a general or acceptable procedures in there. Okay. So in their canonical representation. Okay, so if so they're like in their, yes, I guess it is kind of like related to their accepted representations. So that's acceptable, but these aren't. As an example, the canonical representation of maybe A is either a unit. Oh, interesting. Which makes sense. Yeah, that does, because maybe A is 1 plus A, and then this would have been A times 1. No. Does that make sense? I don't know. So, to reiterate, this doesn't mean you should prefer using either A over maybe A. Alright, let's try and break it down quickly. So, either A of unit. So, we know that the left is all it can return, it can't return. So, that's got to be cardinality of... Well, first it was... It used to be... A times, no, either is like plus, isn't it? Yes, so it's a plus. So it's not. It's a sum type, not a product type. So that's why I got confused. Yes. So so if we look like maybe it was 1 because of nothing plus A, but here we're going to do that's 1 plus A. Yeah, same card. Yeah, that makes sense. Okay, that's where it came. For now, it's enough to know that two types are equivalent. We shall return to canonical forms in chapter 13. Oh, okay, well, maybe I shouldn't have looked up what it meant. Yeah, cool. Okay, well, I'm going to leave it for now because I'm hungry. So, thanks for joining, and hopefully see you guys next time. See you later.